Welcome. In this lecture, we are going to talk about counter based DPWM and with Deadtime and Verilog HDL programming. So, in this lecture, we are going to recapitulate our digital voltage mode control architecture, then counter based DPWM and Verilog HDL based implementation, then generation of gate signal and also the dead time, and finally how to implement in Verilog HDL. So, now we are going to discuss the counter based DPWM. And we have discussed this architecture, I think week 2, where we are talking about different type of DPWM architecture. And in this particular lecture, we are not going to close the outer loop. We are only, if you discard this path, that means if you discard this path, we are setting a constant value here, because our objective is to get the generate the duty ratio which is with a fixed frequency clock, because we want to implement this particular part which will generate this duty ratio, and this we are calling as a DPWM and dead time circuit. And we know about the resolution effect, that means what is the minimum resolution, and we have discussed that how to overcome that, if you want, because if you want a resolution of 9-bit 10-bit DPWM or 9-bit DPWM, then if the switching frequency is 1 megahertz, and if you need a 10-bit DPWM, then you need 1 gigahertz clock, which is not acceptable. So, there are alternative architecture that we have discussed. So, now the similar context, because we are just recapitulating what we have discussed. So, that means in order to get certain DPWM, we need to play with the architecture of DPWM. In this case, we are only taking about DPWM counter based, and we have our desired switching frequency for this teaching kit. We are setting TS to be 5 microsecond. That means our TS, or you can say TSW, switching frequency is 200 kilohertz, and we have available controller clock which is 100 megahertz. So, we need a counter DPWM, I can say DPWM. I mean, if you take the number, that means the ratio will be 100 megahertz by 200 kilohertz, and this will be equal to 500. So, we need a DPWM of 9 bit, which can count from 0 to 499, and this we are familiar about this resolution. Okay. So, now in this particular architecture, as I have discussed that we want a fixed control output, that means we are not closing the loop, and we are talking about the sine Q format, and we have discussed that Q format concept in the previous lecture. This is to represent 2s complement binary number. And when you say Q n dot m, that means we want to get n as if like a integer bit, we are talking about n integer bit and m fraction bit. There is no physical fraction because it is a notional concept. That means, if we have 0 0 some 1 0 underscore some 1 0 1 0 like this. So, this is a notional concept which Verilog ignore, but it is just to represent the n number of bits in the left side and m number of bits in the right side, that we have discussed. And we have also discussed, in order to compare two number, because in digital circuit comparison of two number means it is simply subtraction, and we can simply check the MSB, that is enough. So, any subtraction is, we need to ensure the format of this control output and the counter must match. Okay. Now, the next question, so this block we have to design. Now, what is the next question? Our next question is that we know that it is a 9-bit DPWM. Okay, and 9-bit DPWM is a requirement. So, counter will count from 0 to, because this is the counter will count from, so counter will vary from 0 to 499, 0 to 499. But this is a binary number. What is a real life voltage equivalent? That is the most important, because we are talking about a sawtooth waveform. So, like this. Okay. Now, this for counter it is just a number, but in real life this corresponds to some voltage, because if you pass this signal from D to a converter, it should appear like analog voltage. So, we want this Vm to be, let us say, 2 volt and this to be 0 volt. Then the counter is counting, that means for the counter it is 0 and it is 499. So, this is for the counter point of view. So, what should be the Q format? The question is, what should be the minimum size of the counter. So, first of all, we need a positive 2 volt, and the Q format we know, because it has to take the 9 bit totally. So, we need, so for the dot side, what will be M? That means we are talking about N dot M. First of all, we only need positive value. That means we must have a 0 MSB to represent the positive number. So, that means it should be 0 in the MSB side. Then the rest of the bit can be utilized to accommodate the number. So, the rest of the bit, let us say it can be, there will be, that means if it is 9 bit, the other bit will be B0, let us say. Then B minus 1, B minus 2, like that, B minus 1. So, since this, if you take this total is 9 bit, let us say total is 9 bit. So, this 9 bit, if you vary, it is just a number, it is like an unsigned number. So, this can vary from 0 to 499, and when it is set to 499, it is approximately equal to 1 volt, because the integer bit can be 1 maximum and all close to 1. That means, if we set n equal to 2 and m equal to 8, then this counter, and if you make the 0 leading bit 0 and use this 9 bit DPWM, then it can take from, that means your counter, if you say the quantized voltage level can vary from 0 to nearly 1.95 or something, it can be approximately volt. So, it is approximately, that means we want 0 to close to 2 volt. So, for that our minimum bit size should be the Q 2.8, but remember we need to match this bit size. So, but this bit size we saw, if we said, because we will be discussing the control output, this will be 4 bit, let us say it is Q 4.15. Then how do you match? So, in order to match, this counter must have 4 in the integer bit, and where we can simply make 2 additional MSB by sign extension. So, this should be minimum 4.8 to be comparable. So, you need a resizing, and this should, you can discard the bit, so that you can make this bit to be Q 4.8, where the 7 extra bits are discarded, and that we are going to discuss. So, this is what we are discussing, that counter control output, where we are making the module. So, it is a DPWM module, main module, where we are talking about a high frequency clock. This clock, PWM clock at this point is not needed, because we are not synchronizing, but when we go to the closed loop control, it requires, but you need to sync with this PWM. Next, the counter output. So, control output, because in the main block, if you go back to the main block, as if this block is a sub module of the main voltage mode control module that will be discussed in the next week lectures, where this sub module only take controller output and it will generate the high low gate signal. So, in this case the controller output, when you go inside, so this controller output we have assumed, because since it is a part of the digital control and that we will discuss, it is given in the 4.15 format. It is, there is no choice because it is coming from the controller output. And the switching frequency clock we may synchronize, but in this case we are just giving a fixed number and we want to ensure that switching frequency, overall switching frequency will be 200 kilohertz. So, this clock is very important, that is the input. QPWM is input, but we may or may not use it, and the controller output is a vector data, is a sign number input, and then QH, QL are the scalar output. Okay. So, there is an internal variable. So, QPWM is the output of this block, which will be used to generate the dead time QH and QL. So, this will be the base duty ratio clock, the signal, and that will be used to generate the dead time circuit and actual high side low side gate signal. And we need some PWM delay because we need to pass through a delay block, that we will discuss. So, the control output we want to match, that means we are talking about resizing. Now, initially if you go back, this is the initial block input, which is a sub module block. Inside this block, if you go inside this block, we are assigning a variable which is controller output. So, the con underscore out, which was the output of the main block, we are doing resizing to get that we are calling as a controller output. That is why it is an wire variable. And we are taking a counter, and we discuss the counter has to be 4.8 because the 4 bit is the requirement coming from the cont output, that MSB, and 8 bit is mandatory for the counter because we want 0 to 2 volt. Okay. And we are resizing, it is a concatenation operation. Now, in this point we can also define a value because we are talking about just a fixed number. Okay. We can simply take the value because in the next lecture we are going to simulate this. So, always clock edge, that means at the positive edge of the clock. So, counter will start incrementing, and we are taking for the counter from 0 and 1 value, we are taking QPWM 1. That means for 2, that means we are talking about the counter like this. So, for the 2 value, if we consider this is 0, this is 1, this is 2. So, up to 1 the action will be taken in the next cycle. That means we are setting a minimum duty ratio as per this comment, which is 2 is the number minimum and total number is 500 into 100 that percent, and if you do that you will get 0.4% duty ratio, that is my D minimum. We may set minimum value, we may increase the minimum value, does not matter, but we have to make sure that whatever we want, whether we want minimum duty ratio or minimum duty ratio can be 0. So, then counter is incrementing. Then next the counter, as long as the counter output is lower than the controller output, because the next will be we have a controller and this is the controller output, and if we take this signal, okay, then so this we have to take. So, this will be your Q, this is your QPWM. So, whenever the controller output, that means this is my controller output, as long as the, and this is my counter output. As long as counter output is below the controller output, the PWM signal will be high, when it crosses it will be low, and this is exactly what is meant for. So, when it up to this point it is high, when it is equal to 499, that is the reset condition. So, this is 499 and this corresponds to 2 volt. Then roughly 2 volt, approximately I would say approximately 2 volt, then it will set to 0, counter will reset, and else that means when it goes above the PWM output is 0 and counter will keep on increment. So, this is the Verilog code and the dead time. Now, we got this QPWM, which is this QPWM, which has a duty ratio dt, but we cannot send in the real circuit because there has to be a dead time. So, that we must avoid any overlap period. We have to provide overlap period of the rise time and the fall time of the high side and low side switch. That is why we have to provide the dead time. And this dead time, if you look at this, whenever the controller, the PWM output goes high, then you have to first turn off the low side switch, which was on, because the switch was off. Now, we have to turn on the switch. So, that is why we have to first turn off the low side switch. It is a break and make. Then you have to provide a delay and then you turn on the high side switch. And when you get the falling edge of the PWM signal, then you first turn off the high side switch, then provide a delay, then you turn on the low side switch. So, this is called you need a dead time circuit. So, that this time is called dead time. So, during this time you are actually avoiding turning on and off of the simultaneously two switch. So, that means, but this time should not be too large because it will otherwise actually turn on the body diode and that may lead to reverse recovery and other losses. So, you have to be very careful, and if it is too small, there can be a condition both the switch can be on and that may be high induced current. Okay. So, how to generate this dead time circuit? If you go, we are delaying this PWM signal. That means, if I pass this QPWM through a delay block, so delay block, and this delay should be customizable, then we are talking about PWM delay. So, the signal is named and you can see it is delayed. Now, if you look at this waveform, how do you synthesize? So, QH and QL, how it is generated? TD, that is the dead time. Okay. So, let us say so clock frequency, we can use the clock frequency. So, that means, the resolution of this TD will be some n number of delay into T clock, time period of the high frequency clock. So, it is an integer multiplier because you cannot get better resolution than T clock, it is defined by the T clock. So, if your PWM switching controller's clock is slower, then you cannot actually have a precise control over the dead time. So, you need to have a high resolution clock. So, now this dead time, then from the waveform, what is QH? You can see it is, that means I am talking about the QH high side gate signal will be QPWM and PWM delay. That means QPWM, so you take QH, it is the AND between these two signal, because if you take this region and to this region, they are simply ANDing operation when both are on. Okay. So, this is simple. What about QL? So, QL if you take, that means this period and this period when both the switch should be off. That means, when both are off, then only, that means if let us say we have a and B, if both are off, then only it will be high. Then what will be this? This to be OR A plus B and not of that. So, it is basically NOR. So, NOR of this. So, QL is the NOR. So, QH is the AND of two signal and QL is the, that means QH is basically the AND gate. That means, it is AND that we have written, and QL is the NOR operation of what? QPWM, comma PWM delay, and this is exactly is written here. That means, if you write this Verilog code delay generation, So, delay has to be use a shift register. That means, there is a clock. Whenever this edge clock comes, this signal is propagated to this side, and this whatever was there, it will propagate like this way. So, suppose if the clock edge come, so if you take if you take the waveform, let us say we take this waveform. So, suppose we have this clock frequency, okay. Suppose we have this clock frequency, so this is the f clock. Suppose your input clock is like that, let us say it was high, like that. Then what will be this signal? Let us say it is A, B, C. What will be A? A will be delayed by 1 unit. That means, this edge come. So, this will be our this clock. It will be delayed by 1 unit. What will be B? It will be delayed by another unit. So, like that way, the out will be delayed by 1, 2, 3, 4. 4 unit delay. You need 4 shift register. Okay. So, number of flip flop or basically D flip flop here in this case will be the total delay will be number of flip flop minus 1, because if you take, so 1 will be delayed, the next will be delayed. So, we are using how many from shift 0 to shift 4, that means 5 unit delay we are using 1, 2. So, there will be 1 shift register, 2, 3, 4, 5. So, delay will be 5 shift register delay. So, that means, we are taking the tau d to be 50 nanosecond the delay. Okay. And this can be, that means, we have discussed that if you have this QPWM, then we just generate this delay. And what is QH? We know that QH is the AND operation of the QPWM and the delay signal, and the QL is the NOR operation of this signal. So, you can simply write a code to do that. So, in one line you can write, that means, assign QH, this is in data flow modeling which represent the AND gate, and this is a NOT of OR operation. So, this is a OR operation and this is the AND operation. Okay. So, AND operation, OR operation, and this is a invert, that means, you are complementing this. So, this now the end of this module. So, in summary, we have discussed, we have recapitulated the digital voltage mode control, we have talked about counter based DPWM and Verilog HDL implementation, we have discussed generation of gate signal and with dead time, and we have also discussed what is the Verilog HDL implementation of gate signal generation. So, in the next lecture, we are going to show the live simulation of the part of that means, we want to check the behavioral simulation of this DPWM and the gate signal. That is it for today. Thank you very much.